Our next section in the study of the Lebesgue measure is approximation. So in this section we will present various results on approximation of measurable sets by topological sets in the context of the Lebesgue measure. So by a box in Rn, we mean, so n bigger than or equal to 1, okay, we will mean a set B of the form product j equals 1 to n ij, where ij is a finite interval one less than equal to j less than equal to n. Okay, so each ij is an interval, and so if ij equals ai bi, an open interval, aj bj, 1 less than equal to j less than equal to n, then we say B is an open box. If ij equals aj bj, closed interval, 1 less than equal to j less than equal to n, then we say B is a closed box. If ij is a semi open interval for all 1 less than equal to j less than equal to n, then we say, they call it half open box. So if B is a box, Mn of B obviously is equal to product j equals 1 to n M1 of ij. Also, it is clear that given epsilon positive, we can find boxes B1 epsilon, B2 epsilon of any desired kind, open, closed or half open, etc., such that Mn of B minus B, such that B1 epsilon is less contained in B contained in B2 epsilon, and Mn of B minus B1 epsilon is less than epsilon, and Mn of B2 epsilon minus B is also less than epsilon. So you just have to move the boundaries a little bit for the box, and then you will have whatever you want. So now recall that how would the Lebesgue measure come? You had this ring R from these boxes, semi-open boxes, half-open boxes. P is half-open boxes. Then we had the ring, and then from the ring we went to the hereditary sigma ring generated by this, which is nothing but the power set of Rn. And there, so from the measure here, we had the natural outer measure from which we got the measurable sets, which gave you the Lebesgue measure. So, so we will use this notation mu star, and whenever we say measurable, I mean Lebesgue measurable sets, okay? Because there are also Borel sets or Borel measurable sets. So measurable will mean, unless otherwise specified, Lebesgue measurable sets. So proposition, let n be greater than or equal to 1, E contained in Rn, any set, then mu star of E is equal to the infimum over mu star of U open and U containing E. So you take all open sets which contain E, the infimum of all that will be the mu star. So the open sets more or less determine the outer measure. Okay, so proof. Nothing to prove. if mu star of E is infinite. So assume mu star of E is finite. Now E contained in U implies mu star of E by monotonicity is less than or equal to mu star of U. So therefore you have mu star of E is certainly less than or equal to inf mu star of U, U containing E, U open. Okay, so now let epsilon be greater than 0. So by definition of outer measure, there exists half open boxes Bn such that E is contained in union n equals 1 to infinity Bn, and sigma mu n of Bn, mu star, which is the same as Mn, okay? Mn of Bn, n equals 1 to infinity, is less than mu star E plus epsilon by 2. Okay, so now construct open boxes Bn dash n equals 1 to infinity such that Mn of Bn dash minus Bn is less than epsilon by 2 to the n plus 1, okay, and Bn is contained in Bn dash, of course. We just saw that you can do that, okay. Then U is open equal to U and n equals 1 to infinity Bn dash is open. U contains E. Further, mu star of U, which is the same as Mn of U, is less than or equal to sigma of n equals 1 to infinity Mn of Bn plus sigma epsilon by 2 power n plus 1. So this is equal to sigma Mn of Bn plus epsilon by 2. So we have E is contained in U open, and mu star of U is less than now mu star E plus epsilon, because you have this and you have this, and therefore you have mu star of E plus epsilon. So this implies that mu star of E is equal to the infimum of mu star of U, U open, and U contains E. Okay, so that completes this proposition. So now we have a proposition which characterizes Lebesgue measurable sets. So let E be contained in Rn. The following are equivalent. One, E is Lebesgue measurable. 2, for every epsilon positive, there exists a U open, E contained in U, and mu star of U minus E is less than epsilon. 3, for for every epsilon greater than 0, there exists F closed, F contained in E, and mu star of E minus F less than epsilon. 4. There exists a G delta set, capital G, such that E is contained in G and mu star of G minus E is 0. And 5, there exists a F sigma set, capital F, such that F is contained in E and mu star of E minus F equal to 0. Now, G delta set is nothing but a countable intersection of open sets. A countable intersection of open sets need not be open. So, that such a set is called a G delta set. It's in the sigma ring, of course, of the Borel sets. Now, F sigma set is countable union of closed sets. Again, countable union of closed sets need not be closed. It's called an F sigma set, and again, it will be in the sigma ring generated by the open sets. Okay. So, proof 1 implies 2. So, mu star E, assume, is finite. Then there exists a U open by the previous proposition, U containing E, and mu star of U is less than mu star of E plus epsilon. We just saw that. Okay, but then everything is finite, and therefore you have mu E is Lebesgue measurable, U is open, therefore Borel and hence Lebesgue measurable. So mu star is same as Mn for U and E. Okay, so that's where we are using the hypothesis. Then, you know, measure is subtractive when you have things are finite. So you have mu star of U minus mu star of E is less than epsilon, but this is nothing but mu star of U minus E. So what do you do when, so if mu star of E is plus infinity, then mu star is sigma finite, in fact mu star equals Mn is sigma finite, and there exists Lebesgue measurable sets En such that E is contained in union n equals 1 to infinity En, and mu star of En or En, which is equal to Mn of En, is finite. So there exists Un open, and you have that mu star of Un minus En can be made as small as you like. Let me say is less than epsilon by 2 power n. Then you take U equals, and Un of course contains En. So U equals union n equals 1 to infinity Un, and therefore U is open, counter union of open sets is open, U contains the union of Ens and therefore it contains of E, and then you have mu star of U minus E is less than or equal to mu star of union n equals 1 to infinity Un minus En, and that is less than or equal to sigma epsilon by 2 power n, which is equal to epsilon. Okay, so this completes the proof of 1 implies 2. Now 2 implies 3, 2 implies 4. So for each n, choose Un open such that E contained in Un and mu star of Un minus E is less than 1 by n. This is the statement number 2. Okay, statement 2 is for every epsilon that exists open set such that u mu star of u minus epsilon. Now we are, see, the first one alone we say Lebesgue measurable. After that we do, that is equivalent statements. So here we are only using the fact u star because we don't know a priori that E is Lebesgue measurable. Okay, so then you have that G equals intersection Un, n equals 1 to infinity, and then this is a G delta set, and G contains E. Okay, and mu star G minus E is therefore less than or equal to mu star of Un minus E, and that is less than 1 by n. Okay, and therefore this implies that mu star of G minus E is 0. Okay. The third, then 4 implies 1. So 1 implies 2, 2 implies 4, 4 implies 1. So these 3 statements become equivalent. So Lebesgue measure is complete. So mu star G minus E equal to 0 implies G minus E is Lebesgue measurable. We have seen this already. And therefore, now G is a G delta set, implies Borel measurable, implies Lebesgue measurable also. And then E is nothing but G minus G minus E. G contains E, and therefore E equals, and this is Lebesgue measure, because all these operations are closed in any ring or sigma algebra and so on. So therefore this implies this. Now we want to show that 1 implies 3. So E Lebesgue measurable implies E complement Lebesgue measurable, because it's a sigma algebra. Okay, therefore there exists a U open, U containing E complement, and mu star of U minus E is less than epsilon. So F equals U complement is closed, and therefore U contains E complement, and this implies that F is contained, U complement is contained in E, and therefore F is contained in E. Okay, and then mu star of E minus F is nothing but mu star of E intersection F complement, which is equal to mu star. But what is F complement? It is nothing but U, mu star of E, which is equal to mu star of U minus E complement, and that we know is less than epsilon. So this proves, so if you have E is Lebesgue measurable, then because of the previous we have that this is true. So then 3 implies 5. So for every n, choose Fn closed. Fn is contained in E, and then mu star of E minus Fn is less than 1 by n. And you take F equals union n equals 1 to infinity Fn. Since all of them are in E, this implies F is contained in E, and F is a F sigma set. And mu star of E minus F is less than or equal to, because this is a union of all of them, and if I take only a smallest thing out of it, so this is less than or equal to E minus Fn, is less than 1 by n. So this implies that mu star of E minus F is 0. Okay. Finally, 5 implies 1. So F sigma set, F contained in E, mu star of E minus F equal to 0. So this implies again Lebesgue measure is complete, and therefore E minus F is measurable. And then E is containing F, and therefore you can write E equals F union E minus F. Okay, and therefore this is measurable. So this completes this thing. So we have various equivalent forms of, so you can approximate. So this says E is Lebesgue measurable, then you can approximate it by means of an open set from above. That means the difference between the two is a very small measure. Similarly, you can take F closed, so you can approximate it from inside, so that mu star of E minus F is less than epsilon. Okay. Or you can just find a G delta set whose measure which contains E, and there is no measure between the difference between the two is of 0 measure. And finally, similarly for a F sigma set. So these are our various characterizations. Next, we will investigate the approximation by compact sets, so that we will do next time.